Okay, perfect. That was part A. Part B. The whole thing, what was part B? The laminar one? Part B, what is the laminar part of the boundary layer? Okay, so what's the heat transfer in the laminar part? So in the yellow one, as per this drawing, right? So that means that I need, you know, to grab the local heat transfer coefficient on every single stretch of this yellow portion here, sum them all up, so that I can have, what will be the final heat transfer coefficient for all this portion here. And if I sum up every little portion of heat coming out of every little single strip that I just drew here, then I'll get the total one. Instead of doing that, what we do is we get the average, right? So we sum everything up with an integral, we divide everything by the distance we're interested in, and that gives us our average. So I'm going to take the local coefficient at the very end of my layer, of my laminar portion in this flat plate, and I'm going to divide by this distance here. That's going to give me my average coefficient, and with that I can calculate my heat. That is the game plan. So I'm after my average from where we're going from the boundary, from the leading edge to the, we know already, what was it? 0.14, 13.45 centimeters, right? All the way to, so from my leading edge all the way to the 13.45 centimeters. That's the average that I'm looking for, correct? And I know from things we already see in the channel that we need to do, if I get my local one at 13.45 and I double that, then I'm going to have the average for that yellow region that I'm looking for, right? That's where the Nusselt equation we saw before with the 664 comes from. Okay, so that's the game plan. Find the average one, with the average find the Q. Okay, so we can do, or there's a couple of options here. We can do the same one if we want, find the local one with Nusselt like so, and then with that we can double it. That's one option, or we can go straight into the average, which is going to be double this. It's really up to you guys what you prefer. So if I'm doing Nusselt at 13.45, or we can just do x critical to make our lives easier, then obviously Reynolds is going to be Reynolds critical, and we know everything, right? So that means that my Nusselt at x equals x critical will just be equal to 0.332 times Reynolds critical, which is 5 times 10 to the 5th, square root of that, and then 5.41 to the 1/3. And this gives us about 412. Okay, let's not lose track of what this is. This is exactly the Nusselt at the boundary, right? So now if I go and grab my coefficient, that's just going to be my Nusselt, 412, times my conductivity, 619, divided by x, and x critical is 0.1345. Gives us about 1896.12, keeps going, so I'm going to go ahead and approximate that to 1896 watts per meter square per Kelvin. Okay, now again, like I said, let's not lose track of what this is. This is the main thing here, is that you guys understand what's going on, right? Not that we get the right numbers, but that it makes sense. What we just found is, if I draw a green line here, we just found the coefficient for that, for this green line here, right? So this is the coefficient at x equals x critical. What I want to do now is I want to find what is the average. So what will be the average of all these coefficients from the leading edge all the way to that? And I know that that's just going to be double the local one, right? So if I want to find what is the average one, I'll just take double 2 times the local one. In this case here, my average is just going to be 2 times this, 2 times the 1800, which is 3792. Okay, remember, this makes sense. Remember, because it starts, we talked about this before as well, on the leading edge, that's where we have, quote unquote, the least resistance, least thermal resistance, and the H is higher, and then it drops. And it's going to grow again only when we reach the turbulent part there. So, in other words, this point that we found here, right, this one here, which is H at x critical, is smaller than the one at the boundary layer, so x equals 0. Correct? So that means that our average should be somewhere here in the middle, which is going to be greater than the one we found. yet smaller than the one that we would find before. So this should be smaller than the one we found at 1 centimeter. Where is our 1 centimeter? Here it is, 6,000. Yeah, 6,900. That will be closer to the leading edge. So it's about 6,000 over here. It's about 1,800 over here, 1,900 over here, and then the average is actually about 3,700 or 3,800. Okay, that's where we are at. So if I want to know what is the heat transfer for the laminar portion, I'm going to take the average of the laminar portion, which we just found, and multiply that by the area, multiply that by the difference in temperature. The average is the one we just found. The area is it's not 0.5, it's just this distance here, right? So it's just this distance here, which is from 0 to the 13 centimeters that we calculated before. And the width, obviously, is going to be the same width, so the 0.6. So this is going to be 0.6 times the 0.1345, and then my difference in temperature remains the same, the 40 and the 20, which means that my Q for the laminar part is 6,120.67. It keeps going, so 6121 it is. 6121 approximately in watts. Okay, you might get slightly different answers, slightly different numbers if you round it differently, but at least it should be something close to this. Cool. Part B is done. Part C. What are we looking for in part C? Lost track of it. Let's see. Part C, we're looking for the local heat flux at x equals L. So we want to know what is Q at x equals L. What is Q right on the edge there? To do that, we need to find what is the convection coefficient at the edge. So same story. C, we're looking for Q at x equals L. What is it? So to do that, we're going to have to find H at x equals L. And we know that at the end of this plate, we have a turbulent flow. And what are the two possibilities in terms of equations for me to use? Because I know I'm looking for turbulent. So for the turbulent, we have the local one, right? So the local one, which is 0.0229. And the other one that we saw before, where is it? Here it is. Yeah, so 0.3. So this is the same thing here, 0.029 Reynolds local to the 0.8 times Prandtl to the 1/3. Okay, so these are the two options that we have here. If I'm looking for the average, I would say this one, but I'm looking for the local, right? Exactly the one at the point of interest, which is x equals L. So this is the one I'm interested in using. So to do that, what I want to do is I want to find Reynolds for that. I actually already did find Reynolds. If you recall, we found Reynolds at x equals L in the beginning of the solving of this problem, somewhere here. Where are we? Here it is. Reynolds critical. Here you go. 1.86 times 10 to the 6th. So all I'm plugging is these guys here. So what I'm looking for is what is my local Nusselt at x equals L, which will be 0.029 times 1.86 times 10 to the 6th to the 0.8 or 4/5, Prandtl 5.41 to the 1/3. So I got Nusselt to be about 5,386. And then we can go ahead and calculate what is. We know that our HL will simply be 5,385 86 times 0.16, the conductivity for the water, and then divided by obviously L, which is 0.5. This gives me about approximately 4 sixes. That's watts per meter square per Kelvin. And then finally, what we're actually looking for, which is what is my heat flux at x equals L. So that's just going to be exactly the coefficient at L and delta T. So in this case, just 6 times my 20. And that gave me about 1.33 times 10 to the 5 watts per meter squared, or obviously 133 kilowatts. Brilliant. Next part D. So in part D, we want the Q for the whole plate, right? Q for the whole plate. And to do this, well, I'm aware that we have a mixed situation in the whole plate, right? So we've gone over this, that we saw that there's a laminar portion and there is, so mix, I mean a laminar portion plus a turbulent portion. And so therefore, what I'm after is the equation that relates exactly the mixed one. And note that I'm looking for the average one, so I'm getting the average Nusselt, so you can get average coefficient, average H, for the whole plate. So now if I want to take, what's the energy coming out of this whole plate, I'm after the average thing for the whole one, and this is an equation I use for the mixed case situation. We happen to already have the Reynolds, right? So we know Reynolds at the end of the plate is, what did we find before? 1.86, the same 1.86 we used on the previous one, times 10 to the 6th, that's going to be to the 0.8. Then Prandtl we know, saying 41, that's to the 1/3, which gives us a average Nusselt of approximately 5,204 units there. Once again, if I'm after my average convective coefficient, I'm just going to take the average Nusselt for the whole plate, multiply that by my conductivity, divide that by my characteristic length, in this case the whole plate, right? So that's going to be 5,204 times conductivity, the 0.619 divided by the 0.5. So divided by the 0.5. And this gave me about 6,442.56, and it keeps going, so let's go ahead and approximate that to 6,443. That's watts per meter squared per Kelvin. Right, so if I want the Q for the whole plate, well, energy for the whole thing, considering the mixed flow that we have, it's just going to be the average one that I found for the whole thing times my delta T times my area for the whole plate, right? So in this case, I'm going to be taking the length and the width, full length, full width. So this is just the number I just found, 6,443 times my 20 difference in temperature times my 0.6 in width and my 0.5 in length, all in meters. This gives me about 38.65 in kilowatts, or obviously, if you want to leave it in watt format, just 0.86 times 10 to the 4th in watts. Cool. So that is part D. Right, and last but not least, E is asking us what is the heat transfer in the laminar, or actually, excuse me, in the turbulent portion of the plate. So at this point in time, I think we just need to recall what's going on, what we found so far. You actually have a tip that's telling you, the Q for the whole plate is the Q for the laminar portion plus the Q for the turbulent portion. We happen to know the laminar, happen to hold the whole one, so that's EDP, right? Just find the turbulent one, we just do the whole one minus the laminar. So therefore, to find the turbulent, we just take the Q for the whole plate and we subtract that of the laminar, which will give us that of the turbulent. So this is 3.86 times 10 to the 4th, as we just seen, in watts, minus what we found it was 6.12. 6.12 times 10 to the 3rd for the laminar one. And obviously, if this happens to be greater than this here, then you did something incorrect. You have to go back and see what you did wrong, right? The whole thing has to be, if there's no turbulent whatsoever, obviously it's going to be exactly the same, but it cannot be smaller than just a laminar portion. So this tells me that the energy of the turbulent part is 3.25 times 10 to the 4th. And that is in watts. Great. So you can do a little, analysis here quickly to actually see what we're doing. Because let me just grab the simple one, this one here. Okay, what we're saying there is, just to keep in mind what we're doing, right? What we're saying is, oops, went down too far. Oh, actually, I have it here. There you go. So we knew how much Q was coming out of the laminar portion. And we know that the whole plate was what we found out on part D, right? If I want the turbulent one, then all I want is to take the full one, the blue and the yellow in this case here, subtract the yellow one, so I'm left only with the blue one. And that's what we just did on this last part here, right? So I hope this helps. One last thing that I want to point out is that now that we know the different individual portions, we can actually find out what is the contribution of the laminar versus the turbulent. And it turns out you can do that quickly, obviously. And it turns out that it's about 84%. Okay, so this is telling you that about 84% of the total heat coming out of this plate and going into the water is coming in the turbulent part of this regime, right? So this means that, if you recall, I actually did it up here, I think, the graph with h, and how h is varying as a function of x, and I told you that it was going to go down in the laminar flow and it's going to shoot up again in the turbulent flow. So the greatest h we have in the beginning, only looking at the laminar right in the boundary, the leading edge, then it's going to decrease all the way until we get to the turbulent, and then it shoots up again, and that's why the turbulent is the main responsible for the heat transfer. And this is again because of the eddies that we have during the turbulent regime that actually are capable of taking the molecules of higher energy away from the surface of the wall, taking them elsewhere. All right, I hope this helped you guys out. If it did, consider liking the video. If not, let's leave any questions below that you might have, and it can help you out, and we'll talk soon.